Thank you so much. And thank you to the Bang Bang Con organizers for putting on this conference and for creating such a welcoming space for new speakers like me and for everyone else. And yeah, let's get to it. Today, I just wanted to share with you like my multi-year saga of repairing my Commodore 64 that I found in the basement of a thrift store, buried in the dust and dirt. And just my experience of going from someone who had some basic working knowledge of playing around with electronics and to someone who maybe has a little bit better of an understanding and appreciation for how these machines worked. So let's talk about the Commodore 64. For those who haven't used one before, it might be a little unfamiliar. This computer was released in 1982. It sold about 10 to 17 million units, depending on who you ask. And that puts it among the ranks of like the top selling computers of all time, I think. So when you turn this thing on, you just get this screen. And this is like a screen that represents a world of like infinite possibilities. What you're looking at right here is an interpreter where you can just start typing in basic code. Like the most common one is the 10 print go to 10, hello world kind of thing. You can just start going. Now you can also plug in cartridges in the back. There's a floppy disk attachment that you could use to load additional software. And I'm sure there were many, many users who never wrote a line of code or never created their own applications, but used the software created by others. And that's perfectly fine. That's perfectly great. But for those who wanted to learn the system a little bit better, Commodore provided a programmer's reference guide. And this guide would basically explain to you, like at a really low level, how all the hardware worked. And if you found that this game that you wrote or the software that you wrote in BASIC wasn't fast enough, well, their programmer's reference guides would also teach you how to write assembly code. And so instead of using an interpreted language, you could write assembly and get so much more performance and interact directly with the graphics hardware on the system. And really like a whole generation of programmers, grew up with this machine and it changed the course of their lives. And so why do I want one of these? Or why did I want one of these? I'm not quite sure. I was a little young to have ever used a Commodore 64 in its heyday, but I knew that it existed. And I especially knew that it existed by way of the demo scene, which is a really fascinating internet art subculture that I just really love. And a lot of folks in the demo scene also love this system. So I kind of wanted one too. Also, I had spent some time studying the architecture of the Nintendo Entertainment System and learning how that worked at a really low level. And that was a really rich and rewarding experience. And so I kind of wanted to do the same thing with the Commodore 64 because they share this very similar processors. And I thought it would be interesting to compare and contrast how engineers, took the same, similar building blocks, but created vastly different systems. And so if you look at these old computers and you compare them to computers of modern times, it's clear to see that everything has gotten smaller, everything has gotten more tightly integrated. And the way that we think about fixing these old computers versus fixing new computers is also drastically different. On the left here, you see an actual photograph of my board. You can see that 2 chips are removed because I was debugging and trying to determine faulty chips. And so I was able to do that with relative ease. And on the right, you see a MacBook Pro 16-inch model. And wow, that just looks so crazy. I don't know if I would ever try and fix a specific component on that thing. And I don't think most people do. Certainly, Apple, has some sort of refurbishment center, and I don't really know how that works. But your average mom and pop computer repair shop probably would throw their hands up at this. Now, there are some exceptions to this rule. A fellow by the name of Louis Rossman, based in Manhattan, runs a computer repair shop, and he is like a wizard. He uses advanced microsoldering techniques, under a microscope, and he'll debug and he'll replace the missing components and repair traces, and it's crazy. But most people aren't going to do that. If you look at a Commodore 64, You would notice that a lot of the chips and a lot of the components on there are bog standard, off the shelf, and it was possible for people back then to repair their own computers. They could buy these replacement chips. There's tons of 74,000 series logic, which is like a de facto standard of the time. And there's off-the-shelf DRAM chips. So if your RAM chip fried, you could, if you were lucky, it was socketed, and so you just pluck it out. If you're a little less lucky, you'd probably have to wrestle with a solder sucker, or if you're, maybe a little bit more wealthy. Today, like you can use a desoldering gun, which kind of automates the process of removing chips from boards. And it's really important to note that even back in the 80s, Commodore provided schematics to authorize like warranty centers and also just their customers. If you opened up the programmer's reference guide that I mentioned earlier, you would see a folded up schematic that you could unwrap, and you would see how your computer was built. Imagine getting one of those now with your laptop. You'd be overwhelmed. And I was overwhelmed looking at this schematic when I got started. It's just, an insane amount of detail. And if you were, trying to fix your old computer back in the day, if you were lucky, one of those standard chips failed. But if you were a little more unlucky, maybe one of the custom parts failed. And that was kind of like your sign that you need to send this off to an authorized warranty center and, let them use their stock of like proprietary chips to repair your system. Today, we don't really have the luxury of buying new Commodore 6510, I think this chip number for the CPU. You'd have to harvest them from some other broken machine and you'd hope that one works. So lucky for us in the year 2020, information has been preserved and it's being shared online. And I think anybody who ever tries to repair a Commodore 64 will stumble upon this individual's website, which is just a goldmine of information. This Ray Carlson, I believe, was a former Commodore repair tech, and he has accumulated over the years tons of documentation, tons of reference material, and it's super critical and super useful for someone like me who is just getting started to be able to rely on the accumulated experience of someone like him. And it's just amazing to me that he has documented this so thoroughly and sharing it for free. So this is all well and good. And if you are experienced, you can sift through this information and you know what to look for. But I wasn't really experienced when I started out. When I got my Commodore 64 in the thrift shop, it looked like this, looked like in pretty good condition. But when I turned it on, I was greeted with not a very friendly screen. You might notice that this looks nothing like that friendly blue screen that we saw earlier. I did not dare use a video clip for this presentation, but if this were a video, you would see these colored dots wiggling and waving across the screen, and the computer was totally unusable. But that didn't stop me from trying to fix it. I took apart the computer. That's a thing that I kind of always do when I get old electronics. I like to clean them up. I like to make them presentable because I also want to use them. They're not just sitting on a shelf. I mean, they sometimes sit on the shelf for a little while, but every now and then I like to pick them up and use them. So here's what my actual Commodore 64 looks like when you take it out of the case. For a beginner, like, this is scary. What are all these chips on the board? What do they mean? How do they interact? And I used Ray's documentation, and I started, trying to get a sense for like what's wrong with this? Like, what part has failed? What parts have failed? I was completely, fumbling around in the dark. You can see here that Ray lists all of various chips and like their failure mode. What does it look like when this chip fails? And all I knew was that I had a black screen with dots on it. He calls them blank screens, and surprise, surprise, there are lots of blank screens. I was overloaded with information. I did not know what was important, what was not important. But I still tried. I went through chip by chip and tried to replace some things. One common thing that people recommend is piggybacking RAM. Basically just taking a replacement RAM chip and sticking it on top of one that you think might be working. And I did that, and of course that didn't work. The sound chip is notorious for failing on the Commodore 64. It's known as the SID. You might have heard of it. And sometimes when that chip fails, it prevents the whole system from booting up. So I plucked that out. No luck. There's another chip that fails a lot. It's called the PLA. The PLA is kind of like a switchboard operator for the system. And if that chip fails, then nothing will work. So I bought a replacement PLA from Germany by some guy, and that didn't work either. So I was just out of ideas. I decided to set this project down and maybe come back to it when I could attack the problem with a little bit more rigor. What I was doing was akin to, if you had a programming project that you're working on and there was a bug, I was basically just changing random things and hoping that something would work. And just like that's no way to program, that's not really a great way to diagnose a piece of hardware that's faulty. So I spent some time working on other projects. I kind of upgraded my tools a little bit. I gained a better understanding for how they worked. And a few years later, I decided to come back to this project. And I decided to take a more directed approach to figuring this out. And the first thing that you need to do to fix something is understand it. So let's take a look at the Commodore 64 circuit board and kind of break it down. Now, there's lots going on. You can ignore all those little like chocolate chip cookie type things, those little capacitors, and the other like passive components on the board. And we can focus on some of the more interesting chips. On the top left, we have I/O. Those are two identical chips, and they are basically peripheral controllers. Next to them, we have a series of ROMs. They store things like the basic interpreter, the kernel that basically provides low-level functionality to the rest of the system, specific routines. A ROM chip that basically just has the character data, so like the actual text that you see when you type. The CPU, that's really important. We also have the SID chip that we mentioned before. Below that, the PLA, the RAM over in the bottom left. Of course, we've got a cartridge connector and the power section of the board. And in the middle, we have like the video section. So you can kind of see that these different components of the board, of the computer, live in their own little regions. And if we think about that, the physical layout of the board, we can kind of map that to the schematic. And so now we don't need to understand the whole schematic in order to, attack this fix. We can maybe take a more directed approach, and we can focus on just the information that's important to us at that time. Now, I don't have any specific like diagnostic equipment for the Commodore 64, although it does exist. So I didn't necessarily know that, for instance, all of my RAM was working and that all of my ROMs, still were returning valid data. I did know that my PLA should be working because I had replaced it. So I decided to first focus on the video circuit. We knew that we were seeing this weird like colored dots. Like, what is that all about? So let's zoom in on that. This is the video region of the board. Normally, this would have been covered with like an RF shield, but none of us have X-ray vision, and I don't have an X-ray display, and I don't think you do either. So like, we have to take that thing off. And we can see that on the circuit board, now you can't see them in this picture, but these chips are all labeled. And so that's really useful for finding out where they exist on the circuit. So U19, this is, I believe, a VIC-2 chip. And so its role is to generate video signal, but it needs some help from this little baby chip, U31. U31 is technically a dual voltage controlled oscillator. Its job is to take a clock signal of a certain frequency, and a clock signal is kind of just like a beating drum. I am not beating with any particular rhythm, but use your imagination. And so U31 wants to take this particular clock signal and slow it down and output that slowed down signal on its pin 6. This clock signal is denoted on the schematic. And all the other clock signals that are relevant to this area of the circuit are also noted. And we can use this information to our advantage. Thankfully, I know I'm in a privileged position to be able to afford an oscilloscope, which is a relatively expensive tool. But these days you can actually get them for a whole lot cheaper. And that's a great thing. So I took my oscilloscope and I started probing around. I measured the master clock signal and that looked fine. And I then measured these pin 6 output on this U31. Pin 6. It's supposed to be 8.1818 megahertz. But it's not. Not on my system. I had this really messy signal. This is not what you want to see. And I knew this chip must be bad. So I bought a replacement. Very fortunate that these things are still for sale. I didn't have to gut one from another system. And so I installed it. Still a black screen, but not a black screen with crazy dots, just a solid black screen. And so that got me thinking, okay, well, the video seems to be good. Let's see if the rest of the system is operating. Now, how can we do that? Well, there are various tools that you can use. Like you could use a multimeter and try and see like, okay, what are the various logic levels of these particular pins? But that's not really the right tool for the job. I use this thing called a logic probe. And I'm going to kind of back and forth on my slides here, but just bear with me. This logic probe allows you to really easily determine if a given signal is a logical high or a logical low. And if you put it on something like a RAM chip on like the address lines, you could see that if you're getting alternating between low and high really fast, this tool will make like a little buzzy sound if it's low or high. And it also give you these little indicators. And so if you see activity like on the CPU bus or on like the RAM, you can kind of be certain that the CPU is doing something. And I wasn't seeing that behavior. What I was seeing, though, is that this signal called reset was being held low on my system. Now, what does that mean? What is reset? Well, if you consider a computer that's turned off and then you turn it on, well, how do you guarantee that the various components in the computer are going to be, orchestrated properly? And how can the system initialize? Well, you need to have a ground state. You need to have a known good state to progress from. And so the reset signal is the tool for the job. If you can generate a reset signal when the computer turns on, you say, okay, well, for the first half or 1 second after turning on the machine, send a reset signal out. And all the other chips will get this reset signal, and they'll know to do whatever they need to do internally. And then we can turn off that reset signal and let the magic happen. It kickstarts off all the rest of the booting process. And on my system, this was not happening. Every single chip had the reset signal held low. So they were constantly in this state of trying to reset. And that's no bueno. So if we take a close look at the reset signal, the reset schematic section of the schematic, we can see U20 here, which is this chip on the left. And we can see U8 here, which is this chip on the right. 556 indicates that this is a 556 timer chip. And don't really have time to get too much into those, but these chips can be used for generating all sorts of cool signals. In this case, the configuration of the 556 timer is set up in such a way that after a power is applied, it will generate a quick blip for the reset to occur. And it passes that reset signal over to U8, which is an inverter chip, which kind of takes like a thumbs up and turns into a thumbs down, or a logical high to a logical low. And the specifics of why that works the way it does is, again, out of scope. But basically, this system was not working the way it should. This reset signal was never being turned off. And so I knew by using my logic probe that the 556 end of the system was working. I could see that for a little while, the reset signal was being applied properly and then being turned off. But if you follow the output of the 556 over to the input of the U8 with a logic probe, you can see the signal. And then when you look at the output, you can see the signal. And the output on pin 8 here was just constantly low. And so that was my sign that I need to replace this chip. So I replaced this chip. And again, I'm not going to show the video, but here you can see me right after the computer is turned on. We have a logical low being output. So all the chips in my computer get that little signal. And a brief second later, it goes to high. And that's kind of reversed from what you might think. But if you just give me a little faith, you can know that this fixed the system. Here you can see my extremely messy setup at home. I have a lot of video game consoles. I really like games, play them when I can. And I was so pleased to see this. I did not hear it because, unfortunately, my SID chip is still dead. But everything's working. I wanted to talk a little bit more about preservation and reverse engineering because that's really important to keeping these old systems alive. And I know I'm running a little over time, so I'm just going to whiz through this. There's folks doing really amazing stuff, dissolving chips in acid and imaging them and learning how they work at a super low level. And we're using this knowledge to create modern replacements of those custom chips that I said had no replacements. Well, now we have modern replacements, and that's fantastic. Fortunately for the world at large, you don't even need to have this original hardware anymore. The folks at the Internet Archive are doing a great job archiving the software and providing emulators that you can just run in your browser. A project that I'm really fascinated by is the Mr. FPGA project, which uses really cool technology to re-implement various computers and game systems in hardware, which is really cool. And that's it. Thank you so much. I just want to, take a moment to say thank you to all the essential workers. They've always been essential. It's just they haven't been properly recognized for that. You can find me on Twitter at Clawson. Thank you so much, Bang Bang Con.